Hello, I'm Akila from CSEA. My topic is Design of Quantum Computing Circuits from the course Cloud Application and Development. The introduction about the topic Rise of Quantum Computing in Solving Complex Problems, Importance of Designing Efficient Quantum Circuits, Limitations of Current Quantum Hardware. Cloud offers scalable access to quantum resources. Presentation overview, the concepts and the tools, the challenges and the future scope about the topic. Fine. First, the quantum computing. It exploits quantum mechanics principles. Qubits replace classical bits 0 and 1 simultaneously. The key properties about the quantum computing: superposition and interference, and ideal for high dimensional problems like optimization. Still in early development, reset into the stages of quantum computing. This is about the quantum computing and the traditional versus quantum computing. The traditional computing uses binary logic gates. The quantum gates operates on probabilities, classical and serial processing, the quantum and the parallel state exploration. In the quantum circuits, execute algorithm using fewer steps, while in traditional it involves in the many steps. The quantum algorithms include Grover and Shor's etc. While in traditional it uses the old models and it involves in the many steps. So the quantum computing is better over than the traditional computing. The quantum circuits basic made of qubits initialized to 0 or 1. Gates modify qubit states X, Y, Z, H and C naught. The quantum circuits are reversible. Measurements collapse qubit state to classical value. Depth and width affect circuit performance. And the importance of circuit design directly affects accuracy and reliability of results. Poor design leads to high error rates. Efficient circuits reduce gate count and depth. Optimization crucial for noise sensitive and quantum hardware helps conserve limited quantum computing. It is the importance of circuit design. Why cloud-based quantum development? Because the limited access to physical quantum mechanics and the limited access to physical quantum machines, the cloud provides real-time access to actual quantum hardware, supports simulation and debugging environments, enables collaboration across institutions and borders, offers scalable compute power for hybrid applications. This is about the cloud-based quantum development. Major cloud quantum platforms. The IBM Quantum Public and Enterprise Quantum Services and the Amazon Bracket multi-provider access with SDK, the Microsoft Azure Quantum, the Q-hash language and the C-hash and the hybrid focus are the Microsoft Azure Quantum. These are the major cloud quantum platform and the Google Quantum AI, deep circuit design and capabilities, D-Wave Leap. These are the major cloud quantum platforms which enables the modern quantum computing. The IBM Quantum Experience, free to access with IBM ID, Qiskit SDK for Python users, Jupyter-based notebook integration, offers both simulators and real quantum processor, provides visualization tools for circuits and results. The AWS Bracket access to IonQ, Rigetti and Oxford quantum circuits. Bracket SDK integrates with Amazon services. Hybrid classical quantum workflows possible. Usage-based billing and simulation support. API for job submission and monitoring. The Microsoft Azure Quantum support QHash and Python via QDK. Azure Ecosystem Integration ML, Internet of Things and DevOps. Partners include Quantinum, IonQ, Rigidity, tools for hybrid application and resource estimation. Focus on accessible quantum development. These are the Microsoft Azure Quantum. The design tools in the cloud. Qiskit, IBM Python SDK for quantum design, and the Google open source quantum library, the QHash, the Microsoft domain specific quantum language, the Ocean SDK, D-Wave SDK for optimization problems, Cloud Notebook for easy experiments. These are the design tools in the cloud. Steps to design a quantum circuit. Define number of qubits, initialize qubit states, apply gate operations, the logical operations in sequence, introduce entanglement where necessary, measure output states and analyze result, simulate and optimize before hardware execution. The example Bell state circuit uses Hadamard H and C NOT gates, demonstrates superposition and entanglement, produces quantum correlated output, widely used in quantum teleportation and crypto test, simple to run using IBM or AWS simulation. This is the example of Bell state circuit. The simulation versus real execution. The simulator, fast, noise-free, great for debugging. Quantum processor, realistic but introduced noise. Cloud allows seamless switching between modes. Hybrid testing improves reliability of results, important for validating circuit. This is about the simulation and the real execution. The challenges in quantum circuit design. The hardware limitations in the quantum circuit design are the low qubit count, short coherence time, and high error rates from physical gates, noisy intermediate scale quantum, which is called NISQ era. Circuit optimization is non-trivial, and trades-off between speed, accuracy, and noise. These are the challenges in the quantum circuit design. The security consideration of quantum computing. The post-quantum cryptography becoming critical. Cloud system must prevent unauthorized access. Quantum cloud services need identity and management. Risk of quantum enabled attacks on classical systems. Long-term threat to RSK and ACC. These are the security considerations regarding the quantum computing. Use cases and applications of quantum computing regarding the cloud application and development. It uses in mostly the healthcare, where it is used for drug discovery simulations, and in the sector of finance, portfolio optimization, and in the logistics, supply chain route planning, and in the field of machine learning, quantum enhanced machine learning models. In the field of cybersecurity, new encryption. These are the applications and use cases of quantum computing regarding the cloud application and development. The future of quantum development in the cloud. Advances in superconducting and rapid ion qubits, more public-private and cloud partnerships. Development of quantum as a service, which is called QaaS models. Development of quantum as a service models. Integration of classical HPC and AI platforms. Democratization of quantum education and development. This involves in the R&D, which involves the research and development, includes the efficient quantum computing. This is the future of quantum development in the cloud development. Finally, the conclusion about the topic. Quantum circuit design is central to algorithm success. Cloud makes quantum accessible and scalable. Platforms like IBM, AWS, Microsoft, and accelerate innovation. The hybrid cloud quantum feature is inevitable. Developers and researchers must upskill for the quantum age. Thank you.